Okay, so let's start. So thanks a lot for everyone attending, and thanks a lot to Joseph to accepting to give this talk. I think it's quite interesting. It's quite actual. Well, I know I've been knowing Joseph for many years, and well, we met each other many times. I will say a few words about him. So he is now a professor at Czech Technical University in Prague, when where he's heading the Intelligent Machine Perception team, and he's also the director of the LEC unit Prague. Well, he's been all around, not only in the Czech Republic but also in Paris. He did a PhD at University of Oxford. Then he was a postdoc in MIT, and well, all these type of things. He's been then a researcher in RIA and so on. One of the important things is that he's also been awarded the 2-year C grants. So a starting grant previously, and then in 2023 an ERC advanced grant. And well, we are collaborating now in several European projects, and well, I think everybody knows about his research. So Joseph, we are really looking forward to your talk.
Thank you very much, Niku, for invitation and for the very nice introduction. So I will talk about today about learning manipulation skills from instructional videos. And in this work, I will sort of survey some of our work in this talk. I will survey some of our work in this direction from maybe last couple of years, and also will mention some of our very recent work, finishing with a just accepted CVPR paper where we heard the decision yesterday. So first, to start with the motivation, and I will also want to say, I will try to finish maybe 10 minutes before 6, so there is time for discussion. But if you have any kind of questions related, you don't understand something, feel free to ask. Please raise your hand. I'm not sure if I'll say, just maybe interrupt me, and I'll try to explain. It's important that you understand sort of what's happening. So if you feel getting lost, just ask. It's important to understand. Okay, so I will start with the more kind of motivation. So you would like to learn from instructional video. So what is an instructional video? So if you want to change a car tire, what you can do, if you don't know how to do it, you can just go online and type, how do I change car tire? And you get a video like this one, where someone is showing to you how to do this, how to operate the individual tools to complete the task, to remove the tire and so on. In fact, if you, for some reason, you don't like the particular video, there are actually many different videos online where different people show it on different car tires and using different tools. So you can actually choose the one which suits you best. In fact, there are really millions of videos online where, in different domains, from car repair to gardening to cooking or even health. So we regard this really as an excellent source of like a playground where we can really look at learning how to interact with the world around us from visual and language information. This is visual plus the narration, what people talk about, what they are doing. And there's the advantage of these videos where people talk about what they are doing. And we can really, the way to think about this is that we would like to be able to extract from a video like this or a set of videos like this and some kind of an instructional manual, which we could then, for example, upload to an augmented reality device and give instruction to a novice user how to complete the task in a new environment. Or, and this is a real industrial application, how to teach a new person how to do a task, or watch a person, whether they are completing a particular assembly task, say, or manipulation task correctly. I mean, an example of real application is an airplane maintenance. And this is important, it's done correctly, and one can imagine having some kind of a glasses where they watch the, what the person sees and check, oh, you've just missed that particular maintenance step. Another application is in robotics, which, this is something actually where we are putting effort in, is that imagine you can then put this some kind of instructional manual onto a robot to complete a task which is maybe too difficult for a human, or, which needs to be done in a dangerous environment where a human cannot go. So in this talk, I will sort of show you some of our recent work in this direction, and it's going to be organized not quite in time. There will be some sort of time component, but the main thing is that it is going to be, as you're going to see, we're going to start by learning from one video and gradually introduce more and more training data in some form. And you will see it's going to be either synthetic or at the end, we are actually going to generate training data using generative models. And as you will see, we'll kind of also do less 3D. I think this is not necessarily a requirement, but at the moment, at least, that's the techniques which we use. We start with techniques which have a lot of 3D information, a lot of kind of inductive bias in, and only use one video, and then gradually, add more data and remove the explicit 3D modeling. So I'll start with the first work. I may go a little faster at the beginning to have sort of time to finish some of the later and some of the more recent work as well. So the first one I want to really acknowledge, this is work of outstanding PhD student Katerina Zorina, who is graduating. I think she's going to be graduating this year. She's be looking for positions and postdocs. So really the goal is, given an instructional video input on the left, to output a manipulation policy, like a skill transferred on a real robot. And the way we go about this is that we actually extract a 3D trajectory, as I was talking about, like a really explicit 3D modeling of both the person and the tool, as you can see, and then use that as a guidance for learning policy in a simulated environment, which then the learned policy in simulation can be transferred to a real robot, which then transports material in a real, in this case, it's in the lab. And how do we go about this? So the input to the approach is the input instructional video. This is actually from internet, really, and from YouTube, and the simulated environment, which corresponds to the task. In this case, the goal is to transport this material by a tool, which is the shovel here, to this box here. And what's important, that this environment comes with a sparse reward. And the reward is how many balls, how much material I transport from this source to the target environment. So that's the input. Then we have multiple steps, which I'll explain. And then at the end, we learn a policy based on this input, which we will apply on the real robot. The algorithm or the method has 3 steps. The first step is extracting the 3D trajectory from the YouTube video. For this, we've designed a technique which really takes the input instructional video and outputs the trajectory, 3D trajectory of the person and the tool. And the tool is very important, is here modeled as a stick. And it's not just the trajectory, it's also the estimate of the interaction forces between the person and the ground. These are the yellow arrows, and the person and the tool. In fact, there are also the white arrows are estimates of the moment. So there is like a linear forces in yellow and moments in white. So here is an example. We have input instructional video, and then the output 3D trajectory of the person and the tool, which is here modeled using the simplified model as the stick, and with the estimate of the forces. Here are some other examples of like here spade manipulation, again, from the top, and the 2 different viewpoints at the bottom of the same extracted trajectory. Because we are in 3D, we can observe the trajectory from different viewpoints. So this is a technique which we use here to extract the trajectory from the video. And what's interesting is that here we use the person to estimate the trajectory of the tool, but then when we apply the trajectory to the robot, we actually discard the trajectory of the person. So we only focus on the trajectory of the tool, and that's actually an important part of the component. So we don't have to worry about morphology of the robot, because we really care about the trajectory of the tool, which is the spade here. And at the same time, modeling the person is very important to get the tool out. So that was one of the findings, is that just getting the tool out of the video in 3D is very hard by itself. It's just the vision perception task is too difficult. It's a thin object. So we use the person to help us localize and track the tool in 3D, but then we discard the person and only focus on the tool. So the next step after we extract the trajectory of the tool is that we align the simulation with the video, the simulated environment, because we have these different components. We want to align it with the video in 3D. And the way we do it, we don't use any recognition of the object, but we use here the trajectory. What we care is completing the task. We use the goal is to find the scene layout of the simulated environment such that we maximize the number of transported balls from the source to the target box here. So the goal is to align the simulated environment with the video in order to complete the task, to transport, to maximize the sparse reward. The problem is that this is it's a difficult task. The space of the different arrangement is very high. So we actually use the trajectory of the tool to help us to guide the sampling process. So we kind of sample different scene layouts guided by this trajectory. So we extract like some kind of key points on this trajectory, which help us project them down, which help us to provide candidate locations for the objects in the environment. So once we do that, we have a trajectory which is aligned of the tool, which is aligned in the environment, so it transports at least a little bit, like one ball maybe, or from the source to the target. And then the next goal is to learn a robot policy. But what I mean by robot policy is really the velocities of the different motors on the robot, on the different joints, in order to, again, to maximize the amount of transported material, in this case, still in the simulated environment. The issue is that if you apply directly reinforcement learning, it just doesn't work because the reward is sparse. So it's the too hard optimization problem in the space of the robot. So here and this is exactly where we use the video as to guide the learning process. And how we do this is we use trajectory optimization, which is one of the standard tools in robotics. So we formulate the following optimization problem, where the goal is to obtain the velocities of the joints on the robot, which are here shown in red, over the different time of the trajectory, together with the base of the robots. We also optimize where to put the robot in the simulated environment, together with the sort of joints, velocity of the joints of the robot. And we optimize a cost function which is summed over the trajectory, different times of the trajectory. The first, which is kind of the data term, is that we would like to imitate the target tool position. So we like to optimize the joints so that we can follow the demonstrated tool trajectory from the video, which is captured by this term, together with some regularization terms to constrain the speed of the robot and to respect the joint limits. And it's important, it's subject to the constraints of the kinematics of the robot. So this can be solved by sort of tools, standard robotics tools. We use these two packages, which are excellent. I highly recommend them. They are being developed still actively by our colleagues from the robotics community at CNRS in Toulouse and at Paris. And we use that to solve this optimization problem. And it provides us really the initial trajectory of the robot, initial policy, which will transport some material, and then we fine-tune this policy using reinforcement learning. So we use that initialization, then use reinforcement learning, which the goal is to now maximize the sparse reward RT over time horizon H with this diminishing factor gamma, so that the further time steps matter less in the policy. And we want to find the parameters of the policy theta, so that we here really maximize the sparse reward, the amount of transfer balls. If you solve this problem directly from without an initialization, doesn't work. So one needs the initialization from the video and using the trajectory optimization in the space of the robot. So this is the algorithm. So here we tested on dataset of 3 tasks. So these are different YouTube videos for 3 different tasks. These are the different rows: spade, hammering, and using the site. We have 3 different simulation environments. And here are the results for the different environments. What we are the green is and on y-axis is the reward achieved. Red bar is what's considered success in that environment. Green bars are our final policy, and you can see it's sort of better than if you just use the tool aligned with the environment, which is a different step one of the algorithm, and the initial policy learned by just the trajectory optimization in orange. And what's important that the sparse reward basically in many of these environments does not find anything. If you just use reinforcement learning on the sparse reward, if you engineer a dense reward, which is here shown in gray, which, Katerina spent a couple of days doing that, which is the standard practice in reinforcement learning. People really do engineer rewards separate for each of the tasks. You can achieve similar results if you do that, but we are showing that we can achieve similar results to manual reward engineering, but using just the demonstration from the video. And because really we are using the trajectory of the tool, not the person, so we can really apply the same algorithm to different robot morphologies. And these are the different policies learned using robots with different morphologies, 7 degrees of freedom, 6 degrees of freedom, or even a humanoid, upper body of the humanoid with 11 degrees of freedom. And we can measure the reward using in the spade environment on these different robots and also achieve sort of similar results. So this is an example of really learning from instructional video how to achieve a fairly, and the task is difficult. I haven't stressed that at the beginning, is that because it's so dynamic. So, you really have to, it's not easy to kind of manually program this kind of a dynamic manipulation task. At the same time, one of the key limits of this work is that it's really only limited to these stick-like tools, like a spade or a hammer. So we don't really, which can be modeled by this sort of stick in the 3D environment. So, what we are thinking, well, how can we really handle really three-dimensional objects in this manipulation, not only sticks? So the second work I would like to talk about is, and this is a line of work which we've been kind of following for several years now on estimating accurate poses of objects in images. And I will specify that in more detail. And the main point of it I will kind of show now is that we can actually pre-train this kind of a 6D object extractor on a large collection of synthetic images, as you'll see in a little bit, and then apply it to a completely unseen object at test time. But the main goal is to enable, and this is work of Jan Labe, who's graduated last year, and Israel has been the main driving force for many of these papers. And so just to have a problem formulation, so we have an input scene like this one, with just several objects, and we have a 3D models of those objects available, which is an assumption here, but often in robotic setups, it is the case that you are kind of manipulating or need to manipulate objects which you know ahead of time. And the goal is then to estimate really the accurate 6D pose, which means camera translation and rotation with respect to the camera, between the object and the camera, so that if you then know, if you have a calibrated setup where you have a robot, in that coordinate system, you can then manipulate the object. So now if you say, I want to grasp this object here, you can recognize where it is, recognize its pose, which is here is estimated poses of the objects, and you can then essentially program a manipulation trajectory which will grasp that object if you know its 6D pose with respect to the coordinate system of the camera and the robot in this case. So we've developed a method which I'll not go into details, which can estimate these 6D poses of objects in images. On the top is input image, predicted poses overlaid of the objects, and this is the 3D visualization of the scene. And these are some of the standard data sets, images from some of the standard data sets on this problem, which is called the BOP challenge. And you can see that the algorithm actually from single image can estimate poses of fairly complex scenes. So at the time, which is in 2020, this algorithm, which is called COSI-POSE, was one of the best, or was the best performing method on this problem. And we've kept building on it, and I will show some of the improvements. And and by the way, so the algorithm is available online. You can use it, and some researchers in the robotics community have been using it also. We've also made an extension to articulated objects, where the goal is to not to estimate only the pose. In this case, the object is a robot with respect to the camera, but also its articulation. So we will be not 6D pose, but 6D plus, say, if you have 7 degrees of freedom, you'll be estimating 13 parameters, which would be the camera, the camera translation rotation, and the 7 degrees of freedom. So this is an example of given input single frame when we estimate both the pose and the joint angles of the robot. So it can be applied to articulated objects. So, but in all these works, what we assume is that we have the object, the CAD models of the object available at training time. So we would require to train a render and compare method, which I will show you in a bit, but the method has required the objects at training time. And this is somewhat inconvenient because you kind of retraining the network may take time. So every time you bring a new object, like, this cub here, I would have to go back and retrain the whole method, which may take a day, or maybe at least update the network with this object. It just wouldn't work on objects which you haven't seen at training. So what I want to show you now that we have this method, this paper has been published at Coral, which was in December 2022, which can now be applied in this setup where I actually have I have a still CAD model of the object, but not the training. I just come in and I directly start using the model with a new object for which I have a CAD model. And really the key kind of ingredients to that was a pre-training the model on a very large data set. And in this case was synthetic images. And so I'll explain you how we did that. And these are some examples of these rendered scenes which we used for pre-training the model. So what's the setup we operate in? We start with you can't call it training or pre-training stage, where we train the model on a large database of synthetic images, where we have a set of CAD models, large, tens of thousands of CAD models, and we render millions of training images with these CAD models, and we pre-train the model. And then at inference time, we have a new CAD model, which we've never seen before, in this case, these scissors. And now we have an input RGB image, potentially optionally a depth image. And then we can estimate the pose accurately, the pose of that new object, the virtual CAD model, the scissors, with respect to the camera. So that's the setup. And then potentially, once we have the pose of the object, we can plan a trajectory, which will say grasp the object or do some visually guided manipulation. So that's the setup. The method has these 3 steps. And I will try to speed up a little bit here so that we get to some of the more recent work. But really the key ingredients is large synthetic training data, and then we have a coarse estimation stage, which estimates approximate viewpoint. So here the input image is here, and we have a roughly approximate viewpoint, which maybe is not quite correct. And then we have a refiner, which is a neural network. And this is, again, neural network, which approximates coarse viewpoint, and a refiner, which estimates the fine viewpoint of the object with respect to the camera. And I will kind of zoom through this a little bit. So we have a data set of 2 million images, which is composed of 50,000 scenes captured from different viewpoints in scenes, and each scene is composed of 40 objects, sampled randomly from a database of 50,000 objects, which is from ShapeNet, and then several databases. And what's interesting, these are like high quality renders, which we see here. These are rendered scenes. And then we can really use that as a training data to train these 2 stages, the coarse estimator and the refiner. And the coarse estimator, it's really a binary classifier, which takes an input crop of the image, like this one, and then renders a bunch of views of that new object and decides which one is approximately the view depicted in this image. We apply this classifier a bunch of times to get like the best approximate view. And I just want to stress, it's important to treat this as a classification problem. We've tried for a while to treat it as a regression problem, where we would output the pose given the view. And this doesn't work because of the symmetries of the object. So it's important to treat it as a classification. And I will skip some of the details of how we generate training data to train these classifiers, and then move to the refiner step, where we use a render and compare strategy, where we really, given an input image and some initial pose, we render the view, then input it into the refiner, which is a neural network, which is trained to predict an update of the pose, where the pose constitutes a translation and rotation with respect to the camera, 6 dimensions. And then we get a new pose, which we can render using a renderer, which is a standard sort of a rendering for a mesh, and compare it again with the input image using the refiner, which predicts another pose. So in this iterative manner, we output a final aligned pose of this model. This works very well. It's using all the contours of the object. And in this case, it's really applied. One of the innovations was that we use a multi-view representation, which renders multiple views and then predicts the update based on this. It was important to make it work for unseen objects. And here are some of the results, on the 7 different data sets of the Bob challenge. It works for even partly occluded objects. It's been trained on this data because the training data includes partial occlusions. And it does well on the Bob challenge results in 2023 version of the challenge, which was run last year and some was announced at ICCV. This method, which is called Megapose, has been awarded the best open source method on this particular setup of the problem for the unseen objects. Here are some of the example results. I'll maybe skip some of the trajectories. This is how the method for unseen object, it can you can see track its pose. What I want to show is an update of this kind of a new work where we build on this component of 6D pose estimation and really try to build a controller, robotic controller for that. And so it's kind of still, I would say, toy setup. We are not addressing a real I would say, robotic manipulation task yet, but I think it's an important step towards visually guided control. Here, just to understand the setup, we have a camera which is mounted on the robot. So it's a robot gripper here. There are robots in 3 different poses. And there is a camera mounted rigidly attached to the robot, which is viewing the scene. So these are the images on the right from the camera on the robot. And the goal here is to follow the object, so that we would like to have a policy which, when you move the object, the robot is programmed to follow that, but in a 6-dimensional space to preserve a certain translation and rotation with respect to the object. In general, you could imagine once you have that, you can now define a policy with respect to the object, the 6D, the 6D coordinate system of the object. But at this time, it's sort of following the object. And so we really kind of create this perception control loop where there is a perception block here, which I'll explain in a bit. There is a controller which is controlling the robot here, and the robot has a camera on the top which produces images, which are sort of fed in by this green line, input image IK into the perception module, which is composed of 2 steps: a 6D pose localizer, which you just seen, this is what we call 6D pose localization, and a fast tracker. And what's important is watch the colors, is that these systems, they operate at different frequencies because they are, they have different complexities. So the magenta is typically this pose estimator operates at about 5 Hertz. That's the speed we can run these neural networks and this refiner. But this is not fast enough for really a accurate control. So we have a tracker which operates at 30 Hertz, which is using kind of contours, and it uses the temporal continuity. But then we have a optimal control solver which plans the trajectory, which operates at 100 Hertz. And then we have a sort of really, to get like a 1 kilohertz control of the robots, we have a sort of linearized simplified controller which is based or tightly coupled with this optimal control solver, which produces the position and the velocity of the, which produces the torque control. So this is here tau, which is torque on the robot, and gets as input gets the position and velocity of the different joints. So for these things, we use kind of somewhat standard building blocks from robotics and optimal control solver, which again gets the input, the current position and velocity, and produces the target control to say reach the object that on that kind of level. But what's new here is the perception module, which combines the pose localizer and the tracker. And in order for them to work kind of together, we had to devise this time delay corrector, because kind of once you estimate the pose in 200 milliseconds, the object may be already somewhere else. So the pose is kind of old in a way. So how we do that, we kind of use this tracker as a kind of which tracks the object all the time and then accumulates in this buffer the multiple pose updates in the images. So once the pose localizer produces the pose which is kind of old, we can quickly update it using this time delay corrector. So it's really, we had to in order to make them to work at the free, it's a little bit implementation detail, but it was important to really make it all work together. I can answer questions about it if you wish, but I want to move on here and to show you kind of what we can do now. So what you just seen that I will maybe pause the video. We have this setup of camera mounted on the robot, and the goal for in this part of the video is to really be in a particular fixed displacement with respect to the object, both in translation and rotation. So when you throw in the object into the scene, the robot kind of quickly goes into this particular position. Now, when you take the object and you start moving it, the robot wants to keep and maintains the relative pose with respect to the object. If you start rotating it, the robot also, estimates accurately at this 100 hertz, estimate the pose of the object and 6D pose of the objects and maintains the position. Of course, this is somewhat toy setup, but now you can actually define a control policy with respect to the 6D pose of the object. Say if you want to grasp it from a certain location, you can now define a policy with respect to the object. This is shown for another object here, which again, you can sort of move it, and the robot sort of estimates very quickly the pose, does the control at 1 kilohertz, using a torque-based controller. That's why the trajectory is smooth, so that we can do a task. In this case, there are some simple grasping tasks. We can kind of do a simple handover of kind of an object held by a human based on the estimated 6D pose. So that's we are at the moment. We are kind of continue. We really think it's important to sort of integrate the now very good perception with very good control in order to achieve interesting manipulation tasks. So we're continuing this line of work with adding more complexity. So that's where we are at. We can also, once we have the 6D pose, we can do other things like multi-contact task and motion planning. This again work of Katerina. I will probably kind of only show you the result and move on to so that you see some of the latest work at the end. So in this work, the goal is to solve the tunnel problem, if you wish. So a complex multi-contact task and motion plan where the goal is to put this object through the tunnel. So you have to kind of re-grasp the object to do it. And so many of the current task and motion planners wouldn't complete the task because they wouldn't be able to plan this regraph. But now we can guide this with a simulation here on the left with with a demonstration by a human. And the demonstration only includes the contacts that we know that the person has grasped the object and the 6D pose. And we can use that to guide a task and motion planner so that now the robot can actually easily complete the task. And what's kind of a little bit under the hood is that there is and I'll skip some of the details, we're building on a standard RRT planner, rapidly exploring random trees, but we use the demonstration, especially the contact states. When the person is changing the contact state on the object, like grasping, we use that to start additional trees in this to grow multiple trees, and we start additional trees at the places where the human is grasping the object, and it really helps to solve a complicated task and motion planning task, which are sort of guided. And again, we don't care about the morphology of a human, only when the human is grasping the object. And I will I will sort of finish here this part of the work and move on to the last part so that we still have some discussion and questions. I'll try to cover this in the next 10 minutes, is to really focus on learning the reward functions. So this is, these sorts of the instructional video. So here we kind of do interesting things with the robot using kind of a single instructional video. And at the same time, and maybe lots of pre-training using synthetic training data. But really, what we would like is to be able to learn a complicated task from raw instructional videos, maybe potentially many instructional videos. And one way to formulate this task is running reward functions automatically from the video for the perception. And so this is work of Tomáš Souček. And so the way we approaching it is that, I will kind of not quite show you that we can really guide, or drive the robot by, random instruction videos from YouTube, but I'll show you steps towards that, what we are doing. And the way we want to formulate this is by learning how human actions, change the states of objects. And what I mean by state of an object is that, imagine you want to pour a coffee. So the pouring action, which is in the middle, shown by a few examples. So each row is one sort of example, which changes the state of the object from empty cup. The pouring action changes to the full cup. So we would sort of notice the structure. So the object is state 1, empty on the left. Then there is an action happening on the object by a human, and it goes to another state. In this case, a full cup on the right. So there is this causal structure that the action is changing. First, you have a state 1 action, and then state 2. And we would like to do that on a large scale. So the goal is that given a large set of input videos with maybe noisy video level labels, that we know that this set of videos, maybe 1,000 videos, contains, how people cut a pineapple, another 1,000 videos or several hundred videos scraped from YouTube online, that how to people cut an apple, and maybe how to do another task. We would like to learn the action, like cutting in this case, and the different states of the object. That there is a initial state, and we don't know the vocabulary, the names in natural language, but we know that there should be initial state, then the action, and the end state in those videos. And we would like to do it for multiple tasks at the same time. And of course, we like to do it with minimal supervision. And in this case, what we show that we can actually do quite a lot with only kind of very weak supervision in the form of these causal ordering constraints. I would like to extract changes of objects which are caused by actions. And this we can use as a constraint to learn from video. And the motivation is really, if we could do that on a large scale, we could then potentially use those discovered or learned changes of object states as potential reward functions, because then the robot could say, well, okay, have I changed the cup from empty to full, or have I not? It would be still a sparse reward, but we would like to use it as a reward function. But it's hard because the videos, there's a huge visual variability in those videos. These are examples of inflated balloon. I mean, you look at the visual variability. The videos are long. The YouTube video may have 5 minutes where people do different things, talk about it, but maybe talk about other things as well. And of course, it's in the wild, uncurated data. So, people cutting apple actually will get videos where people are cutting all different kinds of things, including, Apple iPhones, for example. So it's a very noisy task, but yet we've kind of demonstrated that one can actually, only using these fairly weak set of constraints, and I will not go into details, we can actually learn these initial states, actions, and these final states from the video. And that's one contribution. We have this weakly supervised learning, self-supervised algorithm, which kind of only using these constraints learns really classifiers for the object state, initial, end state, and the action. And we investigated different architectures to do that in this multitask manner. And we can do that for many different objects and many different actions. And we also formulated, obtain a data set to do for this problem. And here are some of the results where we go from the initial state, the action, and the last row is the end state for different tasks like tortilla wrapping, t-shirt dyeing, or paper plane folding. And we've shown this, actually, you can do this on multiple different data sets. There are some like change data sets, our new data set, but also there's a coin data set, which is also data set of instructional videos. What's interesting is we can learn these kind of state classifiers on those data sets and then transfer them in a zero-shot manner into ego data, like Ego 4D or Epic Kitchens. And they actually work reasonably well. I mean, there are some of the quantitative results. We can measure how well we actually recognize the learned classifiers in self-supervised manner, how well they recognize the individual states and actions. These are the numbers, and compare it with some other methods. And we can also show the zero-shot setup pre-trained on the change it or the coin data set, and then how does it transfer into the Ego 4D or ego-centric data sets. And finally, what I would look at in about last 5 minutes is the latest work which just got accepted to CVPR, where we said, well, wouldn't it be great if we actually could generate images corresponding to the next state? And the motivation is, imagine that you are at this input, you are a robot looking at, this pineapple, and then you're tasked to peel the pineapple and put it in the blender, and then make a smoothie out of it. So how, you would like to ideally, have some visual representation so that you can actually recognize that, how that final state should look like. And this is an example where, given an input image, we can generate how, the object in that another state could look like, but in the context of this scene. In my robot, I would like to see how should it look like, the final, configuration I'm supposed to do in my environment. So that's exactly what this model is doing. Or for an avocado, how it would look peeled. So this is the peeled on a chopping board in a blender, or if you do a smoothie out of it. So it's kind of a generative problem where, given an input image, you like to modify it to change the state of it while preserving the environment. So, and it's difficult because you exactly want to just change the state of the object based on the language instruction in this case, but keep the context of the scene. So here is an example of input, and I would like to have a frosted cake with strawberries around the top. This is output of our method where we modify this cake in this environment, and these are just to to illustrate the difficulty of the problem. I'm showing you results of some other state-of-the-art methods for this problem. That, like, this is another EFD-DPM, which it does the prompt, but it does not respect the context. It generates another cake with which is not necessarily in the same environment or the same cake. Similarly, if you have a person needing a dough on a cutting board, our method, given input image, produces this, sort of preserving the environment, whereas the other methods, they can do maybe plausible, apart maybe from the fingers here, setup of the scene, but it's not the same scene, it's in a different environment. So the goal is to really change the object state, but just the object state, and keep the context of the scene is another example. So how do we go about this? So we have two contributions. The first one is a data set of annotated image triplets for this problem. And here we really build on the previous work which you've just seen, and have a large scale data of instructional videos, use the self-supervised method to identify these triplets of images, initial state, action, and final state, and combine it with an image captioning model to give us language descriptions of these states. And then in the second contribution, we design a method, a generative model, which is extends the control net setup, where, given an input image of the initial state and the text prompt describing the final state, avocado house on the chopping board, it learns how to produce this image. And it's some parts are frozen. I'm going quickly, these blue ones, but we are fine-tuning the pink ones on this data. So we actually really synthesize a training data set of videos. These are the same because they are extracted from videos. These are the same objects, but changed states. And you can use the data to train this model to do the same, to change the state of the object, but preserve the scene. We also had to do some architectural modifications. Here, the control net using typically just the edges or some information extracted from the image. Here we use the the sort of initial encoder from the stable diffusion model to represent kind of the semantics of the scene. We found this works well, and it's kind of easy to train. And then second thing is about the noise in here, and this is kind of, I'm showing it here. We found also it's important to preserve the scene, to use the initial input image as a part of this initialization. And this is kind of, if you use less noise, so we just initialize with the input image, you kind of end up with the same, you don't change the image at all. But if you add more noise into it, eventually, you kind of generate a different scene. And, there is a sweet spot where, you can really preserve the scene, as you can see in the viewpoint you preserve, but you change, from the dirty pan, which is here, to the clean pan. And, we've compared to other previous methods, and they really, they struggle to do that because they have not been trained on this data, whereas we really have created a data set of these triplets. And I will finish to show you some of the results of this, is that really we can generate, for a specific scene, we can change it, say, from a person wrapping a tortilla on a plate, so we can generate the kind of what the action would look like, and then the final state. Or pouring beer, we can generate the action and then the final state, given the input image, which is essentially preserving the scene. So we can kind of generate how the change would look like in this scene context. And with that, you've seen kind of our work in this direction of learning manipulation skills from video, starting by really transferring the skill from a YouTube video to a robot, extending it to three-dimensional objects and estimating their pose, and using that to guide task and motion planning to complete complex manipulation tasks. And finally, not quite yet on the robot, but hopefully we'll get there, is to actually, how to not only change the pose of the object, but also its state. And of course, I do like to combine it with pose estimation to model objects not only by their poses, but also their states. And we can then use it as potentially reward functions for robotics. I thank you very much for your attention. I'm very happy to answer any questions you may have.
Okay, thank you, Joseph. Really fascinating work. So, guys, I just you can raise your hands, or you can just ask Joseph directly. I think the work is very nice and deserves a lot of questions. So let me start. I mean, related to the last work, right? Because you also have a little bit of other assumptions, So you just say, well, I want to do the same activity or the same process for different objects. But then the assumption is that, of course, this process is compatible with the object, because if I put a stone in there, I cannot peel it. So what would happen if you have something, that is not compatible? It will just generate some kind of a peeled stone. What would it do?
It's interesting. I don't think we've quite tried it. Some things, maybe it's for the actions. For example, something is if you put cutting on something which is, like a stone, it would still generate a person trying to cut that. Like, if the action involves an object, for the final state, it sometimes sort of doesn't, I imagine,
yes,
it makes sense. It may generate something, but it wouldn't make sense. And what I want to show, though, here is that, we look at this setup as that two setups. One of them is that categories are seen during the training. It's easier, so the numbers are bigger. I also skip the evaluation, but we come up with this evaluation, which is classification based. So we actually have a real test set of images, and we test how well, we train a classifier, but we train it from the generated data. So the better the generated data is, the better the classifier, and then we classify the images. So if you know the categories, if you train on apples and test on apples, it's good. But then the interesting part is that you do on unseen categories. So there's a setup where we have unseen categories, and then the performance is slower. But of course, there will be still pineapple, and maybe apple is there. It depends how categories are related. This needs more quantification and larger set of categories.
No, I agree. The more data you have, the more likely you are going to get object that looks alike, and then of course you can make this generalization, of course. Okay, so there is a question by Sergio. So Sergio, if you want, you can ask directly your question.
No, it's okay. It's okay. Well, thank you for the talk. Very, very interesting. Very stimulating. But I was wondering whether you've done work on very non-rigid objects, and whether they bring any particular challenges. But I'm also thinking about interaction between people rather than interacting with objects.
And so when you it's very good question, but when you ask it, which kind of, do you mean more the 6D pose or the states kind of which?
Probably I was thinking about the last one, the states.
The states, yeah. I think that the states has a very little assumption actually in this. So like you really, we just kind of find these changes of object states, rigid or non-rigid. It's not quite, you see there was I will maybe bring some of this, in the data examples. Like here, sometimes it's a t-shirt, there's very little 3D, and I think we are going with more data, the better. So at the same time, you don't get much more than a classifier which will tell you, okay, the t-shirt is, state one or state two. So I think, going in between, I think, it's a very good question which you have. Yeah. So I think how we would operationalize it to really, have it on a robot. It's a question, maybe we should start with a subset of the objects which we can really manipulate and know how to do it. I do think a fruitful iron thought will be combining for some, and this may be more the rigid ones, like a 6D object pose plus some kind of a non-rigid part or, complex appearance change related to the object state, which can be modeled in a different manner so that we can at least know where the object is and then apply this object state on top of it. But it's a very good question, kind of a, how it's still going to to robotics application is not easy. So
yeah, I was thinking, for instance, a robot trying to fold clothes in a store.
Yeah, and I think, by the way, one step which we are kind of, we've been trying to do it, but it's hard. But I think I think Tomáš, the student, is more motivated to, I think, he's close to finishing, but he still wants to give it another go, even then for the generation, but is to, at the moment, you can see that these are the different granularities. Sometimes just cutting an apple, sometimes folding an apple, it's a sequence of tasks. You would like to have a model which really can get the individual steps. So if you wish, and we think formulating in this generative manner is actually an interesting one, that it would not generate just the two states. That's what we get training data. But you can think of it as kind of a video or maybe a sparse set of keyframes, which would kind of really, maybe capture the key moments. And I think even for a step towards robotics, I think it's good because it's a step towards a more smooth reward, if you wish. But it's, it's not done. I think it's difficult, but I think it's worth trying. But very good points.
Thank you very much.
Other questions? I'm just curious about, so far you showed examples with static robots, right? I mean, in the sense that, so what would it happen if you apply your approach, let's say, to a mobile robot? Because then you have not only, of course, the manipulation part, but also the robot can change the viewpoint and try to have a look and so on. So you have some more like a first robot view type of situation.
No, it's a very good question. I think it really brings like a whole really robotics in, because you have to control the robot and really have to plan much more complex trajectories. I think on that I would like to show you kind of as one of the maybe final thing. There is a very cool I don't know if I have it actually here. A very cool video from Boston Dynamics where they do some kind of a pose estimation. 6D pose estimation combined with robotic manipulation. I think I have it here. So, they have like, this is the Atlas robot and it's taking parts out, and you see this estimating poses. And I think this is the hard part. And I think that's why Boston Dynamics is able to do that, because they are really, the masters of how to move the robot and you don't have to plan not only the body, the manipulation of the hands, but the body of the robot. Yeah. So I think I like this video very much, because I think the pose estimation capabilities are on the level which we are able to do now. Like it's not something unheard of yet. I think still the manipulation part of it is very impressive. So I will kind of maybe show it as a part of the discussion. The robot is kind of really taking the part, putting it somewhere, and it's not doing much leg manipulation. The next level would be to really kind of move it somewhere, like with the legs. So it's kind of the robot, but it's still maybe using a little bit of the body, has to turn at least. Yeah. So which makes it difficult. Yeah,
but in this way, you could also use what you showed at the beginning, right? Because you have the body of the person, so the person even can just do it like an example the robot can really copy, right? So in some sense, I think this is getting very close to what a human would do, right?
Yeah, and I think maybe one more quick answer to this is that in this task and motion planning, we are also kind of going that direction, not quite, of course, there yet.
Mm-hmm.
One of the tasks which we are looking at is what we call a waiter task, which involves, and I don't know if I have it easily here, but it involves really kind of putting objects on a tray and transporting it somewhere else.
Ah, okay.
So this is like this one here. So here, this really is a so here the goal is to move the objects from here to here. And of course, if you ask a standard motion planning algorithm, they will go one by one. It will kind of transfer the robot here, take the hand and put it here. A human, if you have a tray, you know, they would put it first on the tray of the robot and then
move it back. Yeah, of course.
Move it, you know, and as I, you know, because we now do it, the human demonstrates, yes, you can do it. You can put it on the tray, move the tray, put it there. The robot can then kind of emulating this demonstration can do the same. I'm not kind of showing the video. So it's kind of a, yeah, but it's, you know, but again, you know, for a mobile robot, you have these additional degrees of freedom you have to control, and it's not, it brings additional complexity.
Yeah, but it's already impressive what you are doing. I think it's doing very well, and it's a good, as you mentioned, it's a good step forward to work on this.
But you know, we are excited about this. We, you know, work on this collaborate roboticists, have even a European project which is about, you know, these kind of things. So we are trying to push in that direction at least.
Excellent. Okay, anybody with questions? Oh well. So if there are no questions, well, we are just perfectly on time. So Joseph, really, thanks a lot. It was really interesting, and then I'm really, I'm following your work, and I think it's really, really nice. And I think many of us have a lot of things to learn from this. And I really love this connection to to robotics. I think this is it's perfect for showcasing, definitely, because I think this is what is really missing in computer vision a little bit, right? We just play a little bit around, but this type of robot stuff, I think, is quite interesting.
Yeah, I think
hey,
also
Niku and Josef, thank you very much. I didn't want to leave you hanging, but just good presentation. You put a lot of effort into this, and it's very helpful to give us the intricacies of all of the science behind this too. So thank you.
Thank you. Thank you.
Thank you, Andrew. Okay, good. So, well, thanks again, Joseph, and we'll stay in touch.
Thank you very much.
Okay.
Don't hesitate to reach out if you have further questions.
Of course. Thank you.
Bye-bye.
Bye.